Now let's talk about hypothesis testing. Hypothesis testing is harder than confidence intervals. At the most basic level, confidence intervals you could think of as being fairly easy, actually, because you just do the calculation, say there's the answer, although interpreting them and understanding what they represent is a little trickier for people. Hypothesis testing is definitely harder. And let's start it by thinking about an example. Let's go back to my terrible free throw shooting. Okay, so you know that I've told you that I think I'm about a 40% free throw shooter. Terrible, right? Basketball players, of which I was one back in 6th grade, should be like at least 60% free throw shooter. That would be ideal. Better be 80% or something. But I was not very good at shooting. I'm still bad at shooting. I can't make it into my wastebasket in my office either very well. And so I think I'm a 40% shooter. Basically, I haven't really done tons of experiments. I've done some experiments with it. It seems about right. But you think, Dr. Kinney, I think you're even worse. I think you're a 20% free throw shooter. Okay, you have a hypothesis called the null hypothesis, H0, that you think my probability of making it on any particular attempt, because you've seen me and you've seen how bad I am, you think it's 20% or maybe even less. P is the probability that I make it on any one free throw attempt. I have an alternative hypothesis. I think I'm a 40% free throw shooter, but you say, I'm going to make it easy on you, Dr. Kinney. If you just prove that you are better than a 20% free throw shooter, then I won't press you any further. The alternative hypothesis is that P is bigger than 0.20. Our book uses H sub 0 or H naught. 0 sometimes called not. Don't say H naught. Say H naught. For the null hypothesis. And H1 for the alternative hypothesis, which is what I think is true. You think the null hypothesis is true. I think the alternative hypothesis is true. Other books do use different notation for the alternative hypothesis. H sub A for alternative. Okay. It's not a big deal. That's what our book uses. What is P? P is the parameter that we are testing here. P is my true probability of success. Success being I make the free throw. Now you might wonder, does that probability of success stay constant? Well, in an idealized situation, it seems reasonable to assume it's constant. What's idealized? Like, well, if I'm in a gym and I'm not tired and there's nobody watching me, right? Though if I'm outside and it's windy and people are watching me, a lot of pressure on me, okay, then maybe it's different. Game situation, you might wonder if it's different than practice situation, whatever. That's my true probability of success. It's a population parameter. It's unknown. So again, I'm pretending you think the null hypothesis is true. I think the alternative is true. In fact, I think a little bit more precisely, the alternative is really that P is 0.4. But again, you're saying, Dr. Kinney, if you can just prove P is bigger than 0.2, I'll give it to you. Okay. So what do you do based on this setup of the hypothesis test? You need to actually do a test now. This is the setup of the hypothesis test. How do you actually do a test? You have to do an experiment. Do a random sample. Shoot some free throws. I stand there, do some free throws. How many should I do? I guess that would be the sample size. I guess I could do any sample size, though it should seem a little reasonable, hopefully reasonable, that the bigger the sample size, maybe the more, what's the best word? Accurate the test is, the bigger the sample size. Although again, there's questions about would I get tired, right? If I'm going to do 1,000 free throws, I'll get too tired. Maybe I do 10 free throws a day for 100 days, and I think of that as one big sample of the size of 1,000 or something. But to make it easier to think about, let's make the sample size a little smaller. Let's make it size n equals 20, say. So I do the random sample. I shoot 20 free throws. I count how many I make. Let X be the number that I make. Let X equal the number of successes. So I'm just saying successes here, but I'm really thinking about free throws. What kind of random variable would X be? This should be pretty obvious. Somebody say it. What kind of random variable is this? Binomial, yeah. With n equal to 20 and p unknown early. Who's right? You or me? We don't know for sure. Which hypothesis is right? We don't know for sure. Now, if p truly is 0.2 or smaller, say p is 0.2, you would expect in 20 attempts that I would get 4 or fewer successes. 4 is 20% of 20. So if I get 4 or fewer successes, that's evidence for the null hypothesis being right. If I get 5 or more successes, that's some evidence for the alternative hypothesis being right. Certainly, if I make all 20 free throws, I'm right, right? There's pretty much no chance you're right. P is bigger than 0.2. It's like a miracle occurred. Okay. That would be very strong evidence against the null hypothesis. Even if I make 10 out of 20, that's pretty strong evidence against the null. You might even guess, even if I make 8, that seems like pretty strong evidence against the null. But what if I only make 5? 5 out of 20, that's 25%. Am I right? Well, maybe I was just lucky. That particular run of 20 attempts, I happen to make 5. I was just lucky. If I make 6, I can still see it happening, even if p is 0.2. Make 30%. Once you start to get to 7 or 8 above, then you're like, okay, that seems like strong enough evidence against the null to reject it. But we need to quantify that. There's a couple different ways to quantify it, to decide whether to reject the null hypothesis in favor of the alternative hypothesis. The classical way is what I'll show you first, is to decide on a, here's the word again, level of significance ahead of time, an alpha, and let that define what's called a critical region or rejection region value of X. Maybe it's, if I make 7 or more, I reject the null. Alternatively, I could also compute something called the, wait for it, the most controversial subject in statistics, p-value of the test. Heard of p-values before? Nobody? Raise your hand. No. Okay, a few people. P-values. It's the most controversial subject in statistics, in applied statistics, is use and abuse of p-values in studies. What's a p-value? I'll say it now, I will say it again. And people almost always get this wrong when they're done with statistics classes. Even scientists and engineers get this wrong. The p-value of the test is the probability, p stands for probability, of observing what you actually observe when you assume the null is true. Actually, you have to think about it as a probability ahead of time, but then you compute it after the fact. So you get a certain number of successes. I didn't quite say that as precisely as I should have. It's the probability of observing what you observe or more extreme under the assumption that the null is true. I'll be more precise when we actually compute it here. Okay. If that probability is small, really small, what that means is you observe something rare if the null is true. Therefore, you reject the null. Here's the most common misinterpretation of the p-value. People think it's the probability that the null people think the p-value is the probability that the null is true. That is wrong. Nobody in the world can determine the probability that the null hypothesis is true. It's impossible. I will re-emphasize these things, and I probably will write them down as well, just not right now. Let's do it the classical way first. Decide on classical approach. By classical, I mean like 40 years ago or earlier. Right? 40 years ago is a long time in statistics. Lots of statistics has been done in the last 40 years compared to before that. Classical approach, right? When we're doing statistics, it's almost all math from the last 100 years. Whereas when we do things like calculus, that's like 200 or 300 years old. Doing geometry, it's a couple thousand years old. Classical approach is choose a level of significance. Alpha, which represents a probability. It represents the probability of making something called a type 1 error when you do the test. You are presetting your probability of making a type 1 error. But what is a type 1 error? You could think of it as a conditional probability, the probability of rejecting the null if you assume the null is true. That's an error. You don't want to reject the null if the null is true. You don't want to say the null is false when it's really true. Right? That would be a mistake. It's not a math mistake, it's a decision mistake. It's like in a courtroom. It's like convicting an innocent person. The null hypothesis is that the person's innocent. And in our court systems, right, that's what we assume, innocent until proven guilty. The alternative hypothesis is they're guilty. Rejecting the null is like saying they're guilty. The null is true means they really were innocent. So you made a mistaken decision of sending an innocent person to jail. That's a type 1 error. As a society, we typically think of that as being worse than a type 2 error, which is letting a guilty person go free, acquitting them. Right? Which is worse, sending an innocent person to jail, letting a guilty person go free? Well, people might have different opinions about which one's worse, but since we give the defendant the benefit of the doubt and assume they're innocent, the burden of proof is on the prosecution. We want it hard to make a type 1 error. That means we're intuitively thinking of a type 1 error as being worse. Certainly, it's not good to let a guilty person go free, especially if it's a terrible crime like murder or something. But you can't avoid it sometimes. So what do you choose for the level of significance? A common thing to use is 0.05, 5%. Do you have to? No. People are kind of stuck on 5%. That's part of the controversy with p-values, by the way. People are stuck on 5%. That's the magic number. And I will use 5% here for the sake of illustration, but you don't have to use 5%. You could use 1%, 2%, 3%, 7%, 9.45% if you wanted to. It's up to you. How do you decide? The smaller you make alpha, the harder you're making it to make a type 1 error. So if a type 1 error is really bad, like if people will die if you make a type 1 error, then you want to make alpha really, really small. I mean, literally, if people die if you're making a type 1 error, you don't want it to be really, really small. You can't pick 0, though, right? That's not really a plausible thing to pick. You got to pick something positive. Maybe it's really, really small, like 0.00001 or something. Epsilon. But it's always a trade-off. If you make it harder to make a type 1 error, harder to convict an innocent person, you're making it easier to let a guilty person go free. You're making it a better chance of making a type 2 error. No way to avoid it. Or is there? Depends on what you mean. You can make things better in statistics on both counts by making your sample size bigger. Make n bigger. So you choose the level of significance. For the sake of illustration, let's go ahead and use the 5%. Second thing to do with the classical approach is determine the critical region. Determine the critical region, also known as, AKA, the rejection region. What's that? That's the set of values of X, observed values of X, that will lead to rejection. You got to use the level of significance to figure it out. And how do you figure it out? Well, we got to calculate that probability. And figure out what boundary value of the region will lead to this being approximately 0.05. But how do you do that? I'm calculating this probability assuming the null is true. The null being true includes infinitely many possible values of p, less than or equal to 0.2. How am I going to do that? Choose the boundary value. Choose, I'll call it a boundary value. Assume, for the sake of argument, that p is 0.2. That's called a simple hypothesis. So if I go ahead and do that, I'm really rewriting the null hypothesis to be inequality. Now, in reality, it's not really an equality. It's an inequality. This is called a simple hypothesis. Make it an equal sign. Why is that okay? Because if I compute the p-value for that simple hypothesis, the probability of rejecting the null if p is exactly 0.2, that'll be the highest possible probability for a type 1 error. Because if p were even smaller, like 0.1, there'd be even less chance of being in the critical region to reject the null if p really is 0.1, say, compared to 0.2. There'd be if p is 0.1 instead of 0.2, there's a smaller probability that x is, say, bigger than or equal to 7 than if p is 0.2. I got a better chance of making 7 or more free throws if p really is 0.2 than I do when p is 0.1. So I'm really computing this in the most extreme case where it's as large as possible. That's what I'm thinking about. So if I reject the null, in that case, I'll also reject it if p really is 0.1, say. If that was too fast an explanation, I can explain it again later. So what do we have to do here? I'm wondering, in this certain situation, what value of x, I'll make it a question mark, will make this probability equal to approximately 0.05. I need to find question mark. Find this. There's my assumption that the null is true. P is 0.2 based on the simple hypothesis. What number could I put there that will make this probability approximately 0.05? That's what I'm after. Is it 7? Is it 8? We don't know yet. Let's see if we can figure it out. This would be the same as the probability that x is strict, or excuse me, as 1 minus the probability that x is strictly less than question mark, given that p is 0.2. And so we could use the CDF function in the calculator. And probably we just need to guess. I mean, if we had a table available to us, which we do, we could avoid guessing. But with the calculator, we'd have to guess. Let's just guess 7 and see what happens. So, yeah, let me go 1 minus distribution menu, binomial CDF, n is 20, p is 0.2. I think p is 0.4, but the null is that p is 0.2. If I put a 7 there, oh, and careful, okay, I got to be careful because that's a strict less than. That's the same as 1 minus the probability that x is less than or equal to question mark minus 1, right? Because x is discrete and can take on only whole number of values. So if I put a 7 here, I'm really assuming this is 7, question mark minus 1. So I'm really figuring it out when the question mark is 8. Let's just see what it is. 0.03, pretty close to 0.05. We're pretty close to the right answer. If I do, let's just test the one number smaller. 6. A little bit bigger than 0.05. So we don't get exactly 0.05 for either of these. That's because x is discrete. If I'm going to play it safe, I better use the 7. So it seems like question mark minus 1 should be 7, so that question mark is 8. And what this means is the critical region, also called the rejection region, consists of the numbers 8, 9, 10, etc., up through 20. If I make 8 or more free throws, we're going to reject the null in favor of the alternative. We're going to say that p is bigger than 0.2. And our probability of making a type 1 error technically is a little smaller than 0.05. It was 0.03 something. I was just after an approximation here. Then I actually do the test. I go ahead and shoot my free throws. Maybe I make less than 8. Then we'd fail to reject the null. Maybe I make 8 or more. Then we would reject it. You make your decision. I'll count that as step 3. Do the experiment. And make a decision. Reject the null or not. When you reject the null, reject H0. Is that the same as accepting the alternative? Accept H1. Yeah. Although I will say that most people, when they do the test, just say we reject the null. It's kind of like, not always, sometimes people say accept the alternative, but it's kind of like you're the prosecuting attorney when you do these tests. You think that you're me. You think the null is wrong, and you're trying to prove it wrong. Okay. Gotta be careful. I guess you're wanting to reject the null. Yeah, it's like you're me. The alternative is that I'm worse, or the null is that I'm worse. And the alternative is that I'm better. Usually in a courtroom, it's the opposite way. The null that they're innocent is the better thing for the defendant, at least, and the alternative that they're guilty is the worst thing. So usually in a courtroom, you're trying to, the prosecuting attorney is trying to reject the null. Maybe they really think that defendant is guilty. They want to keep their job. They want to reject the null. They want the court to say they're guilty. And I'm getting this mixed up here. Okay, but if they fail to reject the null, it doesn't mean they accept the null, right? It just means they fail to have enough evidence against the null to convict the person. That's what I meant to say. So you either say reject the null, which basically does mean accept the alternative, or fail to reject the null, which people do not typically say is accept the null. You just don't have enough evidence against it. It's like you're the prosecuting attorney. You don't think that person really is innocent. You just didn't convict them. You didn't have strong enough evidence to convince the jury. That's what I meant to say. Okay, so that's the classical approach. What's the modern approach? And by modern, I mean the last 40 years. The modern approach is to compute the p-value right away. That's step one. Once you set up your hypothesis test. Once you've got the p-value, second step is make a decision. Is the p-value small enough for you to reject the null or not? Done. In both of these situations, you do need to think about the practical consequences of your decision. Maybe it leads to some business decision, like we're going to invest in this new marketing campaign or not. So you need to actually apply it in real life and not just do the theory. Decisions need to be made based on either rejecting the null or failing to reject the null. But what is the p-value here? The p-value, in general, writing it down what I said about 20 minutes ago, but I'm going to be a little bit more specific. It's the probability of observing a test statistic value as extreme or more extreme than what you actually observed under the assumption that the null hypothesis is true. Under the assumption that H0 is true. It's a theoretical calculation that leads to practical decisions. What is a test statistic and what does as extreme or more extreme mean? The test statistic varies depending on the situation. For our example here, effectively the test statistic is the observed value of X. Though it could be modified to be an observed value of a sample proportion, X divided by N, as an estimator for P. If I make 8 free throws out of 20, then I made 40%, 0.4. It could be that as well. That's what we do actually at the beginning of chapter 9 next Tuesday. It could be X, or it could be, when we're testing means, as we will in a few minutes, a value of X bar, or we could convert the value of X bar to a Z statistic or a T statistic. So in our case, we call it a p-value. Let me just pretend I do the experiment and I make 6 free throws. What's the p-value for that test? If I assume I make 6 out of 20. It's the probability that X is greater than or equal to 6, as extreme or more extreme, with respect to the direction of the null of the alternative hypothesis being a greater than. To the right. I need to compute an area under something to the right of something. Under a distribution to the right of 6 in this case. If I make 6, I do this calculation, assuming the null is true, assuming p is 0.2. And that would be the same as this. This should be bigger than 0.03. I forgot, was this one? Let's do it again. 1 minus binomial CDF. Okay, I need to use 5 here. So I'm going to get bigger than 0.08 as well. It's about 0.196. If I make 6 free throws in 20 attempts, the p-value is 0.196 for that test. This represents the probability that I'm going to make 6 or more free throws in 20 attempts if my true probability of success is 0.2. Now, again, calling this a probability is a little bit funny because it's after the fact. Whereas I said probability should be really thought about before the fact. But I mean, you could go back and think of this before the fact. Maybe I'm about to do the experiment again, and I'm wondering, really, if my probability of success is 0.2, and I do 20 attempts, what is the probability that I make 6 or more? Now, that's a small number. Less than 0.5, less than 0.2 even. But it's not really, really small. It's not small enough for most people to reject the null. So we'd say fail to reject the null. Compute the p-value, make a decision. It's the second step. And if that were my p-value in a standard kind of situation, people would say that's not small enough to reject. So we fail to reject the null. Again, it's not that you're saying we accept the null. Not that I'm saying I accept the null. I really think I'm better than 20% shooter. I just don't have enough evidence to reject it. Because this is not, while it's small, it's not really small. What's really small? Less than 0.05 is the standard thing people use. But it's a matter of opinion sometimes. Make a decision, maybe make, based on that decision, to reject or not, another decision in business settings to actually like invest in something or not. Interpret what it means practically. I don't have enough evidence to reject the null. I observed something somewhat rare, but not really rare if the null is true. And you give the null the benefit of the doubt, just like we assume the person is innocent and we don't reject it. If you said reject the null on a test problem when you got this p-value, would I mark it as wrong? I'd say that's not a good idea. And yeah, I probably would take points off. You want it to be, for sure, I think, less than 0.1. Some people say less than 0.05. If it's not that you can't talk about alpha in this context, you can still talk about the level of significance. And if you say alpha is 0.05, and that's the alpha you want to use, and this is bigger than 0.05, then you definitely should not reject the null. You would only reject it if it's less than 0.05. You say this is not statistically significant at the 5% level. If you get something less than 0.05, then you would say it is statistically significant at the 5% level. A little bit more about terminology. The classical approach is often called hypothesis testing. This approach, which really is still hypothesis testing, is sometimes called significance testing. It's when you use the phrase, is this statistically significant at the 5% or 1% level, or whatever you're using for alpha? There's a lot going on here. There's even more that I haven't talked about yet. You got a parameter you're testing, you got to set up your hypotheses. Technically speaking, the null and alternative, neither one in reality is simple, but to do the test, you got to assume the null is simple. You can use one of these two approaches. Both of them can involve thinking about alpha, the probability of a type 1 error, and wanting that to be small. You can think either in terms of critical regions or in terms of p-values. And by the way, with p-values, again, people will often misinterpret this and think it's the probability that the null's true. 20% chance the probability that the null is true. No, don't ever think that. Nobody but nobody can figure out the probability that the null is true. It's impossible. Guess we're out of time. I forgot we ended at 1:30. I thought the class went to 1:40. I was like, I got 10 more minutes. I can't assign as many homework problems as I was thinking of. I do want you to read sections 8.4 and 8.5, and maybe I'll assign one problem or two based on the reading that I haven't gotten to for testing means, one of which involves using a t-statistic. I think I will assign one or two problems based on the reading, but I haven't gotten to it in class.